Because this is section 12.4, which is geometric probability. It should be a short, pretty easy section for you, but I will give you some formulas and stuff later on the back side of the sheet that will help you out a little bit. So geometric probability starts off with talking about a number line. So in an actual problem, like down below here in example 1, they will actually give you values here. So like let's say this unit from A to B is 2, this unit from B to C, let's say, is 3, and from C to D is 4, okay? The whole length of that entire segment would be then, what, 7 plus 2 is 9, okay? And we would then say, like, what is the probability that if I put a dot somewhere on this line, it will land somewhere on BC, okay? BC has a length of 3 out of an entire length of 9, which gives me 1/3 chance that if I throw a dot anywhere and it lands on AD, it will land within BC also. So it's just the length of BC over the entire length of the line, okay? That's exactly what we're doing on example 1. So point X is chosen at random on JM. J is the starting point, M is the ending point, and that entire segment, let's just figure that out, is 3 plus 7 plus 4. 3 plus 7 plus 4 is 14, so it's 14 units long. That's going to be my bottom number. Find the probability that X also lives on KL. So if I put that dot somewhere on this number line, what's the chances that it's going to land within this region on the whole line? Well, there's 7. That segment is 7 units long, and 7 out of 14 is 1/2. So pretty easy so far. And then they throw example 2 at you, which is a little bit more difficult because they don't actually draw out what the number line looks like. So here's what happens. When you're doing this real world example, it says a Chicago Transit Authority train arrives or departs a station like Addison on the red line every 15 minutes. Okay, that's kind of wordy in there, but what's happening here? I'm going to draw a number line that's 0 here and 15 here, okay? This number line is going to represent the amount of time that I could end up possibly waiting for the train. So if I arrive right here, let's say I arrive as the train is coming to the station, I would have to wait 0 minutes for the train, right? But if I arrive right at the end, or like as one of the trains are leaving, I'm going to have to wait another 15 minutes for the next train to arrive. So this is the amount of time that I'm going to have to wait, all right? It's either between 0 and 15 minutes. I'm never going to have to wait more than 15 minutes. And you can't wait less than 0 minutes. So somewhere between 0 and 15 minutes is what I'm going to wait. Now it says, assuming that you arrive at Addison, which is the town that we're leaving from, that's just a random place, on the red line at a random time, what is the probability that you will have to wait 5 minutes or more for the train? So 5 minutes is going to be here, 10 minutes is going to be here. 5 or more minutes is this region from here to here, okay? This whole length is 15 minutes long, and the distance from 5 to 15 is 10 units. So I have a 2/3 chance that I'm going to end up having to wait more than 5 minutes, right? It's more likely than not that I'm going to have to wait more than 5 minutes, okay? And that should kind of make sense given the diagram there. So draw out a number line that represents each one of these real world possibilities when they give it to you, and it makes it a lot easier, okay? Now, in the next example, they start talking about area. So the area probability ratio. What they're going to do is they're probably going to give you like 2 different shapes going on, or maybe like it's one circle inside of another circle or something like that. And it's going to be kind of like a dartboard. So just imagine that I'm taking and I'm throwing a dart somewhere and it's going to land inside of this rectangle, okay? It could land here maybe, or maybe it lands down here. But what I want to do is I want to find the probability that if I have a dot landing in that rectangle, that it also lands in the square, or in the circle, excuse me. I want to know the probability that if I throw a dot, it also lands in the circle. So what I'm going to do is I'm going to find the area of the circle and put that over top of the area of the rectangle. That's going to give me my probability. The area of the circle is the smaller one. That's the more restricted area. And I'm going to divide that by the total area of the rectangle. That's going to give me the probability, okay? All right, so like example 3. Now, they're dealing with circles, and we have area. So one thing that might be a good idea to do is to find the equations for area of, like, let's say a rectangle, and find the equation for area of a circle. All right, these are two that you probably should already know, but if you don't, the area of a rectangle is just base times height. The area of a circle is pi times the radius squared. All right, you probably already knew those. If you don't, you might want to look those over a little bit. All right, if on your homework assignment it gives you the area of, let's say, a triangle or an area of a trapezoid or something that you don't know what the area is, what I'm going to tell you to do is look at your fancy book that you have, and in the very back of your fancy book, I'm at the very last page. It's kind of a thicker material. This is hard for me to show you on this overhead. It's a thicker material, and way down here at the bottom, it has all the areas and surface area of prisms and all that good stuff. So they have area of a square, rectangle, parallelogram, trapezoid, rhombus. I'm trying to say those words at the same time. Triangle, regular polygon, circle, or sector of a circle. So it's got all of the areas that you will ever need. So if on your homework assignment they give you the area of something that you don't know what it is, look in the book for the equation, or you can also Google it on your handy-dandy Chromebooks. All right? So we will need to know these two for sure, I know, for your homework assignment. For this particular example, they are just talking about a skydiver landing on a target of 3 concentric circles. If you don't know what concentric means, that just means 3 circles that are inside of one another. So I have a circle here, I have a circle here, and a circle here. There's 3 concentric circles, 3 circles inside of each other. Don't judge my circles, they're not perfect. All right? If the diameter of the center circle is 2 yards, so from here to here, oh, that's 2. That's really tiny. And the circles are spaced 1 yard apart. So from here to here is 1 yard. Now, if from there to there is 1 yard, then that means this middle circle, here is 2, here is 1, here is another 1. 2, 1, and 1. So the middle circle actually has an entire diameter of 4. So keep that in mind. It's 1 on the outside, 1 on the outside, and 2 in the middle. Okay? The bigger circle is also spread 1 meter or 1 yard apart. So if the middle circle is 4 right here, and this is 1 and this is 1, then that entire length is 6. Okay, so keep that in mind when you're doing these circles. The large one has a diameter of 6, the medium one has a diameter of 4, and the small one has a diameter of 2, because they're spaced 1 unit apart on either side. What is the probability that the skydiver will land in the center circle? So the center circle is the smallest one, and the smallest circle has a diameter of 2. I'll make that a little bit easier to see. All right? So we know that he is going to land inside one of these 3 circles. Okay? So the overall circle that he could land in is this one that has diameter of 6. We know that at least he's going to land in that circle. That's going to be the bottom area. So I'm going to put area of big circle. And what I want to do is find the probability that he lands in the small one. So I'm going to do the area of the small one on top. All right? So we need to find the area of that small circle. Okay? The area of a circle is pi times the radius squared. If my small circle has a diameter of 2, it should have a radius of 1. Okay? You should know that, I think, maybe. So pi times the radius, which is 1 squared, over the area of the big circle. The big circle has a diameter of 6, so the radius of the big circle would be 3. So this would be pi times 3 squared. Okay? Now, before you go and start multiplying all this stuff through and everything, look at your pi's. You've got a pi on the top and a pi on the bottom. They can cancel with each other, so all you have to deal with is the numbers. 1 squared is just 1. 3 squared is 9. So I have a 1 in 9 chance, or a 1 in 9 probability, of landing in one of those 3 circles and also landing in the smallest circle. 1 in 9 chance of landing in that smallest circle. okay? That's going to be your probability. If you want to, you can represent that as a decimal. I don't care, but 1 and 9 is all that I need, okay? So that's example 3. Now, going to the back side, they have one more example back here, using angle measure to find geometric probability. So we have our spinner going on here, okay? And use the spinner to find each probability. Probability of the pointer landing on yellow, okay? You can't tell these, so I'm going to tell you what color each one of these is. The yellow one is the 45-degree one, okay? The pointer landing on purple, I think this one is purple. Give me just a second. I'm going to look in your book. Okay, yep. 105 is the purple. Sorry about that. This one is yellow. Okay, if you look in your book also, you can find these. All right, the 70-degree one is blue. The 50-degree one, this one's red. And the 90-degree one is green. It would help to print these in color, but we're cheap. So the probability of the pointer landing on yellow. Yellow represents 45 degrees, but that's not 45 out of 100. My bottom number is not going to be 100 because it's not 45%, it's 45 degrees. So you need to figure out how many degrees are in an entire circle. And some of you already know that it is, or most of you should know, that it's 360 degrees in an entire circle. If you reduce 45 over 360, it is 1/8. And that's the probability of landing on yellow, okay? Now, suppose, I'm going to do another example down here. Suppose that this was actually 45% instead, okay? That slice of pie was actually 45%. If it was 45%, then it would be 45 over 100, right? Because percentages are based out of 100. So this one is based upon degrees, so you want to make sure it's 45 over 360. The probability of the pointer landing on purple. Purple is 105 degrees out of 360. Oh, lordy. If you divide both of them by 5, I know that works. 21 over 72, maybe. Yeah. But then that will reduce by 3, so 7 over 24. 7 out of 24, I think, is the reduced form. If I did that wrong, you can just fix it, okay? So that's the probability of the pointer landing on purple. Now, the probability of the pointer landing on neither red or blue. Neither is the key word, okay? So let's look at the probability of the pointer landing on red and blue. Red and blue are 50 and 70, okay? Together, that makes 120 out of 360, okay? 120 degrees out of 360 is 1/3. So I have 1 in 3 chance of landing on red and blue. So the chances of not landing on red and blue would be 2/3. You might know that as the complement, or you should know that that's called the complement. Whenever it says not or neither or anything of the negative nature or whatever, do the opposite and then subtract that. So subtracting 1/3 gives me 2/3, okay? And that's basically it, all right? Any of those formulas that you need that you don't already know should be in the back of your book, so look those up, and I will see you tomorrow.